You guys are unmuted, but we can barely hear you. It's very faint. It's still like super low volume. I don't know if it's the same for everyone else.
Yes.
I can barely hear.
Yeah, I don't know why. Like I can hear, it's just super faint.
What about now?
That's still really faint.
Turn up the gain on your microphones, maybe. Technology, it makes our life easy.
Yeah. I see they're using one of the owls. I don't know if it's the owl's problem or whether it's using the laptop mic.
Using the owl, hopefully.
Oh, I can hear that very clearly.
Oh, then it's your laptop.
Oh, I can hear you guys now. It's better now.
You guys are much louder now.
Yeah.
Actually,
Okay, so I guess we are all set.
yeah, let me quickly.
Yeah, so we attempted to have a few, to collect some topics on the Padlet. We can start from those if Thomas wants, or we can freestyle.
We should also add to the Padlet. I can't find it right now. The comments that were made in the discussion from Tassos and others that were probably should not be forgotten. So, thank you, Valeria. Oh, is Tassos there? I can't see who all's there. So,
Yeah.
You better have noted what I said because I don't remember.
it was very, very important.
So one of the things I think we want to also do is start thinking about concrete steps, right? We have been talking a lot now, many telecons now about these pre-LISA, and we identified these 4 topics now, 3.5, 4 topics. And I think one of the things we really want to start is think about concrete steps to get done with, or concrete people we need still we are not on it. I think that's one thing. And I don't know what's the best way to organize this, but we can go through, start with the first project and go through them. Yeah, I don't know. It's
so we're going to mix the pre-LISA and the stellar binaries discussion in this couple of hours.
well,
Is that the plan?
if I look at the schedule,
Oh no, it's just pre-LISA EM. I'm sorry, I've misremembered the whole.
yes. So that's what I assume.
I think it is whatever is useful to the pre-LISA AM group, right?
Yep.
Because we have many posts for stellar binaries and multiples for tomorrow and Friday. We can use these posts.
Okay.
I mean, we can do either way.
Yeah. Well, it says here pre-LISA EM observations, but I think
They're all on stellar.
yeah, they're all on still exactly.
Yeah. So Thomas, maybe I can lead with a question. So I haven't been on the telecons, but this is the first time I've seen the document that you shared. So kind of pertinent to the question that Melanie asked, these are kind of big task projects listed in this document. Are there smaller subtasks that you're looking for people to sign up for, or are you looking to flesh out so that we know what the small tasks are? What's the kind of goal here with what's in this document?
I think both. I think there are small tasks for students who can easily be done. I think, again, this is to me up to the coordinators to make sure to identify them and make sure that, for example, we don't give a graduate student a project where this graduate student will be busy for 10 years. Right. So kind of making, I think both, right? There are big projects, and my internet is not working, so I don't, maybe somebody can share the document. I can't share, I don't see it anymore. Like, for example, I mean, the one Kevin is leading on the instrumentation, that's not something you do in a year. That's a really a long-term project to be ready, right? So that's for sure. But then on the, let me think.
So
Maybe somebody can share.
yeah, I can.
would
The
be
same
good.
Google.
Yeah, I think so. Just as a reminder.
I have it up. I can share if I have permission, but oh, Valeria's got it. Okay.
Yeah, so exactly. So for example, point one, the gravitational wave accuracy with EM priors, that could be sub-projects, right? There could be sub-projects on, let's look at the accreting systems. Let's look at a particular type of binary star. Let's look at the SDBs, for example, something like that, right? So that could be, or like, what does the inclination angle say? So that could be really small projects. And again, that's to me up to the leads then to decide how this is split up, right? So I think it's both, to be honest. And maybe that's something to discuss now also. What do you see as projects we really want to start right now as soon as possible and maybe finish within the next, like maybe something which is even important for the red book. I don't know it. I'm just throwing it out.
Yeah, so I think this is exactly the sort of thing that I think is important is kind of, you know, I'm thinking kind of on two lines. One is the red book, because there's going to be a lot of pressure on those kinds of productions.
Yeah.
But then the other is on projects that students in particular can work on or that we can associate with, because there's enough of us interested in this that there's certainly going to be overlap. And if we put students on these things that'll be related to their PhD theses or something, we don't want to kind of push students one way or the other, just because there's not enough communication about who's working on what.
Exactly. And especially then we also want to make sure that if a student is working on this project, the student is protected doing that work and not some more senior person just running the code. It's much faster, obviously, and just publish the paper and the student is like, oh God. So that's why we also want to make sure, of course, as long as if the people do this outside the collaboration, there's nothing we can do. But if it's within the consortium, within the working group, we want to make sure that this is all
right. Okay. Good. Yeah. So full disclosure, right? Students of mine are in this conversation with us, so they're listening to me ask you these questions, knowing that the stuff's going to get put on their plate. So, yeah. I mean,
I just said it's kind of my personal opinion. I think we never discussed this, to be honest, in the detail, but it's an important aspect. And I think maybe along the lines what you also discussed earlier with Valeria and Marta and you about the other projects where you have kind of some guidelines to make sure that projects are protected. There's kind of clear guidelines on that side. Yeah,
good.
For sure.
Yeah.
And then of course, and then of course coordination. So I don't know if you want to discuss particular projects we think are important right now, or do we want to just generally collect more ideas on the type of projects?
In your previous telecons, have you prioritized at all?
No, not really. Okay. That was really more like brainstorming on the larger scale, like coming up with the projects. We have talked about individual ideas, and there, if you scroll down further down, but we have not done any concrete like planning, right? There's just kind of brainstorming at this point. And so so I want to open the floor to everybody to see which projects they want to see, and maybe we can flesh out some projects where then the lead can take over and make sure to organize that properly. So, now I shut up.
Well, I have one I want to throw out there. Something I'd like to see done is, so we have some of these binaries that are kind of lower frequency, like a lot of the SDB donor systems, where if you look at their LISA signal to noise, it's not particularly stunning. But of course, we already know things like their inclination pretty well. We know their RA and DEC very precisely. We know their orbital frequencies. We know their F dots. And so something I'd really like to see is someone taking one of those where we've already got all of the EM priors and just asking, what can you do with the gravitational wave signal? How much does the information content of that signal get boosted because of everything you've already constrained? Because I feel like right now there's a focus on mostly high signal to noise sources that LISA will blindly detect. But the reality is we're going to get swamped by low signal to noise sources we find in electromagnetic data, where we've got constraints and maybe we can pull something out on them. And those will far outnumber the number of very high frequency sources that LISA blindly detects. So just an idea to throw out there. And we already have sources that people can do modeling for along those lines.
So Kevin, so Tyson and I a long time ago made an estimate of the high signal to noise ratio multi-messenger component. Has someone made an estimate of the low signal to noise ratio multi-messenger component? Like how many are there when you say we're going to be swamped?
Well, I mean, you can just do sort of the estimate of the number of sources coming in and how long they spend at a given orbital frequency if they're evolving according to gravitational radiation. And they spend a lot longer between an hour and 40 minutes than they do 10 minutes and under, right?
Sure. But I guess what I'm wondering, are you talking about sources that specifically have large enough signal to noise ratio to be identifiable as individual sources in the LISA data, or are you talking about the multi-messenger component that's going to be part of the confusion?
Yeah, part of the confusion, unresolved sources, but where we already know the frequency, we know the inclination, and the question is if it were SNR1 or something, according to one of these LISA signal to noise calculators, is there anything I can do with an SNR1 signal from a 40-minute binary if I've already constrained all of these parameters with the electromagnetic data?
Yeah.
And I know the position very, very precisely. Kind of like what pulsar people do, right? They constrain the search space because they might know the orbital period or something already and are able to pick out signals that they would never be able to pick out blindly.
Yeah, that's a good point.
Tyson has a view on this.
Ingrid is sitting here with us, and she has a good example, right? The SDB Y-growth system, which has like a distance precision of, I don't know, 1%, has an inclination precision of, I don't know how many, very, very percent.
Inclination is not super precise.
Okay, well,
but
sorry.
We're getting there.
And this is one of the systems which is kind of,
Yeah.
So Tyson has his hand up.
Yeah, there are, the way I see it on the LISA side, there are two questions to answer here. One is, can you find a low signal to noise source because you have a helping hand from electromagnetic observations? That's a bit of a, intellectual stamp collecting exercise. And then the other question is, do you actually learn anything about it? And if you're already telling the gravitational wave search, the orbital period's evolution, the distance, and the inclination, there's not all that much left that LISA will measure.
Yeah, I guess one interesting one is, say you don't know the inclination. You've got everything else, but you don't know the inclination. How well can you constrain it? Can you get it to within 10 degrees or something?
Right. So those are all good studies, and we have existing tools. Even though I spent a couple hours ago, complaining that we don't have existing tools for this sort of thing we do. And yeah, I think that's a shovel-ready project.
Yeah, and the reason I bring it up is like I'm getting ready to publish more catalogs, and the reality is most of the binaries are not high signal to noise that I'm finding. Most of them are going to be SNR5 or lower. And so one of the questions is, if we accumulate 1,000 of these or something before LISA, when LISA turns on, is there something we can do with those 1,000 low SNR sources?
So Tyson, can I ask you a question?
Just a sec. I'm gonna preempt the results of this study that you're proposing, which is for these low signal to noise binaries. If you want to get something useful out of LISA, we really, really need good distance measurements as well. And if you can provide good distance measurements through Gaia or something else, then there's a chance to get something useful out of the gravitational wave measurement, other than checking the box that we saw that one too.
I see.
What if you have both? If you have a trip mass and a distance, would that help the inclination even more?
Yep. Right. So inclination correlates with amplitude. So the better you can do pinning down the amplitude, which comes from orbital period, distance, and chirp mass, then the better you can do pinning down the inclination.
Okay. I'm already seeing here like several projects popping up, and I'm taking lots of notes. I'm taking tons of notes, and I will put them in a document with specific projects, and then can people talk. So I see Sylvia has a hand up.
Yeah, I just wanted to add one thing, kind of slightly
the opposite of what you were saying, Thomas, for the chirp mass. So, Kevin, am I right to assume that those sources that you have are probably sources where you only see the light of one white dwarf?
Quite
Like
a few of them,
SV1s?
we have both.
Okay, okay.
Yeah,
Well, that's
so,
even better.
yeah.
That's always great. For the ones where you don't see the other component, I would be really curious if then with a chirp mass, we would actually be able to break that degeneracy, right? So if from EM we have the distance, we have one mass, we have maybe something on inclination, then possibly that gravitational wave detection could maybe give us some light on the secondary. And you know, from a modeling side, that is really, really useful to have both masses.
Yeah, I was going to say another problem I've been thinking about are the semi-detached systems. I actually think those are really exciting because one, you can identify whether it's semi-detached pretty easily. If you get any X-ray photons, it's a pretty good chance that the thing is interacting if it's a LISA source. The moment you know that it's semi-detached, the equation of state of all of these donors is pretty well approximated as a degenerate object. Certainly you're going to get the mass to within about 10% if you assume fully degenerate. And so if you have a degenerate donor and you know the orbital frequency from LISA, the orbital frequency tells you the density of the donor. If you know the density of the donor and you have a rough idea of its equation of state, you get the mass of the donor. And then once you've got the mass of the donor, if you have a chirp mass, you automatically know the mass of the accretor. And so you can very quickly pin down accretor masses, certainly to at least the 10% level or so is my estimate, simply by having an X-ray detection.
I think Jan is here. He can probably comment on the donor star ratio and how nice they are fully degenerately, because that's actually not the case.
Not really, unfortunately.
Well, like how far is the deviation though? I haven't seen any that deviate more than like 10 or 20% in their expected mass from a fully degenerate object, at least on the way out.
Radius.
It can be more significant than that. I don't have a number though.
Yeah, I'd be interested in the quantitative estimate.
Let me check that.
Because I agree, they're not all perfectly degenerate. In fact, none are perfectly degenerate. But it's a question of how far do you deviate from degeneracy.
I'm checking just notes.
Can we open the chat? There's loads of comments.
Oh yeah, please. Oh, speak up if we don't. Feel free. Tom has his hands up. Maybe Tom.
Yeah, I want to speak in favor of a limiting number of projects we have, and I think that the project that was mentioned, namely low signal noise LISA sources, would not be my highest priority by any means. If you have a low signal noise, I mean, 1 sigma, you have to divide that 1 sigma up, amongst the parameters that you're trying to determine. Right, and even if you determine all the rest of them from electromagnetic except inclination, how really interesting is that? Because we'll probably have other sources where we will have the inclination from electromagnetic observation. So I would say, we want to maintain some discipline about which projects we do, because we have a lot to do.
I agree.
So, anyway, my 2 cents. So.
We have something in the chat.
Was Mandy on the?
No, we were talking about the availability of tools for these kinds of analyses.
Oh, okay.
But to echo Tom's point there, I think the number of blindly detected LISA high SNR multi-messenger binaries is probably going to be high enough that they'll occupy our attention for some time after we get the first catalog. So
yeah. Okay. Okay.
I have a comment, but it's like sort of on a different topic.
Yeah, I think we exhausted it, so I think you can switch.
Okay, so this is a little bit on a different topic, but I think it's useful also to discuss with the observers. It has been mentioned today that we are also have with the Red Book, mission adoption, etc. We have to deliver a document describing LISA data policy. And something interesting come up in one of these discussions that are ongoing. And that's been like how we are, when we are going to be happy to release LISA data. And one of the comments was that we may be happy to do so if we can recover in the LISA data verification binaries, no, the ones that we know are there for sure. So I saw that this is, I mean, I sort of knew this, but I didn't fully recognize the importance. And I think that maybe for observers, that's an important thing to know, that the binaries that we will be discovering from now until LISA may be, the first test, like actual, and maybe even the first data release, like we don't know, but maybe we will be releasing those sources that we are sure of. Yeah, that was not a question, but
Well, do you know, Valeria, will we get a request from the Red Book team to do something specific on that front? I mean, because they'll want something very precise to provide for the report, I expect, right?
Yeah, I think so. This came within the data policy discussion, so which separate thing, and it was mainly like when are we comfortable releasing data, how, and such.
But that's a good point. So maybe that's a question for the chairs in this room. Is there anything related to the Red Book? And Heis is not here, right? Which we would need to do right now, which we should focus on. Is this something we should ask Heis when he's on? Oh, Tyson, yeah, go ahead.
If we believe the galaxies that we've had to play with thus far, the first sources that LISA can hear are not the verification binaries. They're high frequency, high chirp mass binaries that are screamingly loud and in a part of the frequency band where there isn't any confusion. So they are just unambiguous tuning forks in the galaxy. And I would say that if we're looking for verification and validation of data before releasing it, we might as well use the loudest sources in the bunch and not wait the extra integration time to start digging out verification sources, which are going to be sitting on top of lots of other stuff in the galaxy. So maybe a exploratory project to think about is how we would do some data verification and validation using previously unknown sources that just happen to like blow the doors off of the observatory, and integrate for a couple of weeks, start over again, integrate for another couple of weeks, and do some just basic jackknife style tests to say, does this look like the same source in both epochs of data? If so, then we feel pretty good about it.
Yeah, that would be my question to you, right? So for the verification system we know that these exist, and I trust your capabilities, but what if like how we are sure we are these not glitches, these screaming sources as you call them, or whatever? I mean, not that I have any doubt, but
flaws in the pop synth, right?
That's right.
But also, like some of the verification binaries, HM concrete
are screaming.
Will be screaming.
Yeah, exactly. They are screaming, and have trust in us.
They're screaming
sources.
Yeah, they're screaming sources, but they're screaming in a part of the band where other things are screaming at you as well.
Oh, I see.
And if the universe is cruel and sticks two things on top of each other, you need to get like a full orbit before you can really start to separate these things with Doppler.
I see.
So if you want to do this verification in just a couple of months, there's a good chance of source contamination in the frequency range where we already have sources. At 10 millihertz, according to the models we've looked at, these things are completely isolated.
That's a good point.
But they're not detached likely, right?
So what
Sure they are.
specific? So what specific type of project you recommend, Tyson? Can you like put this again in like maybe one few words that I can make a note?
Data validation that would convince the end user if you don't have an EM source, right?
Okay. Thank you.
Or maybe early data validation is better or adjacent to that, right? Because you're talking about not waiting for a full year of data.
Right.
Yeah.
But related on something that Tyson commented, does it mean that we have to wait like 1 year of Lisa to be 100% sure that we have our known verification binaries? Like,
it depends on how low an SNR you want to go before you consider your collection complete, right?
Yeah.
So if
Okay.
you pick like the 5 loudest.
If you talk like
Right,
this, we'll stop inviting you to these meetings.
Yeah, well, I've got a question. Say ZTF J1539 has another source right on top of it in frequency. We know the inclination of that source from the hypercam light curve to better than 1/10 of a degree. Can you leverage that information because you know exact sources?
Once you get enough of an orbit in to sample both polarizations. So if you want to do it in a month worth of integration because you're really anxious to start releasing data, that's not a long enough integration time.
I see.
Can somebody mute him? No, that's actually really important because that's something I was not aware. That's actually good to know. Okay, maybe let's make sure we cover most of the topics because we have already like half an hour is gone. Maybe we can switch either to the theoretical aspects, like what is like which is kind of what Valeria already talked about, the code comparison, but now more in a line of not better, but more realistic, like including several types of sources, including galaxy models and so on and so forth. And then also I want to make sure we cover at least a little bit the instrumentation side of things, what Kevin is leading. So I don't know, we can maybe start with the theory. But are there any plans, or is there anything people think about, want to do? I mean, that's most certainly a long-term project. That's not something you do within like half a PhD or so.
So there are efforts that are going on. I think to the earlier comment that was made in the other discussion about latching on to Mesa and more modern groups like the Poseidon group are supposedly working on this, on updating their pop synth codes. The BSE version that we use in Cosmic has updated winds and updated kicks and stuff like that. So, I mean, at some level, we probably need to do a survey just to know what updates have been made or what updates people use, so we know where there's uncertainties, right?
Okay. But it's still at this point mostly a individual kind of project, right? So every code does its own little thing, which makes sense because that's what people use.
What do you mean?
Meaning
individual tools.
Sorry, that's what I meant. Yeah, that's what I meant. Individual tools, and everybody does its own thing, which is probably based on what they are most interested in.
Correct.
Right.
There's also very many different angles that you can do, right? So I think there's enough room for the different groups to try to attack these different issues. And I think there's definitely overlap with the project that you presented before with the code comparison, but I think there's also very sufficient amounts of difference, because in the code comparison, you may want to make very simple and easy assumptions that none of us likely believe in, but you just have to simplify the problem in order to start comparing these codes. And I think here, here you actually want to move away from those assumptions and from the easy assumptions and just vary assumptions and see what the effects are on the LISA detection rates and the LISA demographics, right? So there's quite a different angle I think in this group compared to that other project.
Yeah, I agree.
Do we
I mean-
know? Oh, sorry. Go ahead, Thomas.
No, go ahead, please.
No,
Sorry.
I was gonna say, do we know what kinds of EM observations could guide us in those developments? Or alternatively, do we know what sorts of assumptions we're making that can be tested with EM observations now before we actually have LISA data? Right? Is there, right, specifically for this group, right? We're talking about observations before LISA even flies. So there must be interface points with the theory work we're doing in PopSynth that we could go both directions beneficially.
I can think of two right now. One is Valeria's and Nama's approach with SDSS5. And then the other thing I can think of is I think the only survey which, maybe I'm wrong here, but I think the only survey which has a really good space density estimation with population membership is the ELM survey.
Yeah.
And so there we have a clear, right, there's a clear prediction, clear estimation. And so I think those are the two.
How about Foremost?
All right, what was that, Sylvia? I missed that. What?
I said, how about Foremost?
Oh, right. Yeah.
Right, because there will be a lot of double wide doors popping out of Gaia, but then we need follow-up in order to constrain their masses.
Yeah.
Sorry, I think I interrupted Ingrid.
Yeah, no, sorry, I was just saying Foremost is only like 2023 at the earliest. So I don't know how much we can wait for it. Of course, it's still before LISA, but I don't want to sit and wait for a whole year. I want to know what I can do now.
Definitely true, but it's still a significant amount of time before LISA flies.
Yeah, definitely.
And if I think about like I mean, ideally, I want a large population of double wide doors, and actually, kind of Foremost is my only hope before LISA flies.
Yeah, but Foremost won't tell us a lot. Like, he won't tell us any periods, for example.
Yeah.
We will need also to follow up the ones we find in Foremost.
Maybe SDSS5 is even a better hope for that, right? It gives you multi-epoch.
We are also planning that with Foremost, but like it won't be like enough cadence to tell periods, especially the short periods that we are interested in.
Let me maybe ask that differently regarding a concrete project. Is there anything we can do realistically from the observational side over the next few years to provide the anchor points? And don't tell us, give us space density for every type of binary in the LISA fan. That's not going to work, I can tell you. But is there any specific anchor points? Like, what about is TM space density and binary fraction and so on a good anchor point already? And does this tell you anything? Or is there anything else we can realistically do over the next, let's say, few years?
You're asking the theorist what they want to have, or you're asking observation to see what is possible to get?
No, I guess I go more as an observer, ask the theorists what is most useful. Yeah, Valeria?
Yeah, so I would definitely like to have space density, right?
You know, that's the hardest.
It is a sort of like the normalization of the population, but it is the same as Stasos mentioned this morning. Would like, right, the rates is just one number, and you try to compare the multi-parameter population to one number. Has to come with the distributions of parameters, and whatever you can deliver, we can compare, because from our side we can model all of them, right? Yeah, so if the space density can come with the distributions of some parameters, and we have a few that we can start, you know, being in multidimensional sort of comparison, can be cool. Another thing that I haven't seen done, like right, Gaia delivered like amazing HR diagram. I don't know, but can we use HR diagram somehow to our advantage?
Yes, we can.
Okay.
I do this all the time.
And I have a catalog of ELN candidates. based on the
Yeah,
HR
that's
diagram
right.
that I am
Yeah.
following up, try to have a volume limited sample, but it's really hard to do that, especially within a short period of time.
Yeah, so one example is like pretty much everything between the white dwarf track and the main sequence is kind of interesting if you're looking for ELMs, SDBs, whatever. I actually have a test proposal in getting 2-minute cadence on just every object between the main sequence and the HR diagram. You guys can all download that data. I'm down to about 18 and a half. So yeah, we can definitely use the HR diagram in some ways, but there's also a lot of selection bias that comes with that. For example, if you're looking for double carbon oxygen white dwarfs and you're only spending your time above the white dwarf track, you may be looking in the wrong place. And Jan has found, for example, some unexpected eclipsing AMCVNs right in the white dwarf track. But another thing that's interesting is Gaia DR3 also gave us something like 200 million low resolution spectra. I'm wondering whether we could actually go through those and pick out some emission line systems with helium emission, for example, to look for more AMCVNs that way.
Yeah, that might be a good idea. And so I think generally, if we talk about that, as long as we tell the theorists what the selection effects are, you can put that in your code. I mean, technically, right? I mean, as long as we just tell you what it is.
Definitely. Like, I think we're very happy to take into account those selection effects. So yeah, if you have them, that's, yeah, definitely. The problem is usually not us taking into account, but the problem is more, theorists and observers together trying to figure out what the selection effects are.
Yeah.
Yes.
Well, the third part is this, or yeah, go ahead.
Yeah, one thing that I have a question about, Sylvia, is one of the selection effects that we run into all the time is temperature. Okay, so for instance, J1539 is very high temperature. Do any of the codes actually predict the temperature of the white dwarfs?
Yeah, so what we typically do is we get the age from the white dwarf, and then we take cooling curves. And then from the age of the white dwarf, we can estimate what the temperature of the white dwarf is, and therefore also the luminosity of the white dwarf.
Yeah, the question is whether or not that actually explains all the temperatures we see. I think, a 50,000 degree, white dwarf like J1539 is, I think, hard to explain just on cooling curves alone.
Yeah,
what do you mean?
And that's a big selection effect.
It's very young if it's 50,000 Kelvin. And so it suggests that if it was just a cooling age, the CO white dwarf emerged from common envelope at like a 20-minute period and was born second, which is a little weird. I actually still think mass transfer is probably the explanation for why that thing was heated up.
I agree. I agree also. And that's,
So do you asking that? Do your codes include some prescription on like heating, tidal heating, or is there nothing in there? It's probably very hard, right? So,
Usually tidal heating we don't take into account. As far as I know, in these POP-SYN codes is not being taken into account. Shane kind of shaking his head, so maybe someone is.
If it is, I think it's phenomenological, right?
They mess among those. In
Yeah.
theory, it can be done.
Yeah.
In practice, it cannot be done trustworthy.
Okay.
Another thing I wanted to add is, Thomas, you were asking about which, we should maybe focus not only on double white dwarfs, but other populations as well, and which populations then to focus on. But actually, I kind of want to, point out the diagram that Tasso showed and that I also showed about the formation of double white dwarfs and the different stages that we think those sources are going through, right? So for ground-based sources, we talk all the time about using that order to put constraints, right? To look at, black hole O-star binaries to try and get constraints. And I think that the same thing we can do for double white dwarfs. So then the thing to highlight actually is that there's several stages in between, STB binaries there as well. But the interesting thing is then you should also look at white binaries, right? So if you look at Gijs's old work, then we actually expect the intermediate stage to be white binaries. And I think sometimes we focus on compact binaries because those we find with spectroscopic measurements, but the white ones may actually be the ones that lead to double white dwarfs. So that actually gives constraints on, the way that stable mass transfer occurs.
Well, I mean, Gaia will give us tons of astrometric binaries, which are exactly that type of thing.
And then, has already given.
And has
us,
already given us, sorry,
we
good.
can already dig up.
That's a good point. Yeah, that's.
So what about, I'm not up to date on
That's a
this,
good
but
point.
what about the post main post common envelope white dwarf main sequence binaries from like the samples I remember from the last one?
I think Jan can comment on that, right? You
Like,
are very.
what is the status now? Have they been expanded?
Yes,
This can give very clean constraints on common envelope.
that's right. Yeah.
So most of the time, those main sequence companions are very low mass, and the constraints we have so far are really very extreme common envelopes, so very extreme amounts of shrinkage of the orbit. So I'm also really intrigued by, by the follow-up work to try and find these post-common envelope binaries with more massive companions. And, massive meaning, a 2 solar mass star or 1 solar mass star. So still definitely something very common for a white dwarf, but those are hard to observe next to a white dwarf.
They're hiding. Yeah, the white dwarf is hiding there.
Yeah, the best bet may be using something like TESS to look for transits, because it's going to be similar to an exoplanet transit if you have a white dwarf go in front of a G star.
I think there's
Young
also
get a UV access.
Stephen Parsons' work looking at massive stars with UV access. That's also something to keep an eye out for.
The funny thing is, and in that sample, they're finding roughly 50% triples, which may be a selection effect, but they're finding a large amount of triples trying to find these post-common envelope binaries.
That's true.
And I was going to say on the UV axis, something I've heard, I don't know if it's true, is that the Gaia spectra are very well flux calibrated. And they go down to like 350 nanometers. So we should actually have decent U-band photometry in principle from those spectra for the entire sky, which we haven't had before, right? So I don't know if we can also use U-band excess from the Gaia spectra to pick out potential main sequence stars with white dwarf companion, but just a thought, because Galax definitely was not full sky. There are a lot of holes in its footprint.
One thing to add.
Sorry.
There you go, Aikid.
Yeah, the Hot Subgroup community had a look at the blue end of Gaia, and they concluded that it's not well calibrated at the blue end.
Yeah, I kind of figured that would be the reality, but I was hopeful when they sold it as so well calibrated.
The thing I wanted to add about the white binaries is somebody mentioned Gaia for this, but at least when I looked at the 20 parsec sample, the systems that are going to be resolved in Gaia, they're too white. So they are mostly the non-interacting systems. So I think the astrometric binaries are not the ones that are going to help here, but maybe these Valeria, maybe you can explain what the systems that Vasily is looking at.
Oh, that's a difficult.
The Ruby access.
Yes.
Yeah.
So basically, when you look in the Gaia data and you look at the white dwarf sequence and you look at those white dwarfs that have a high, basically bad fit to the single star solution, you sort of can hint that this may be a binary. So, you put 2 and 2 together, you have something that is on the white dwarf sequence or above. It is possibly a binary because the single star doesn't fit Gaia solution. And that's how, thanks to Vasily, we looked at possible double white dwarf candidates.
Yeah.
And with this method, we can actually look at the separation range between 0.01 and 1 or so EU. So it is moving a little bit farther away from the usual, photometry and spectroscopy.
Yeah.
So it's sort of like complementing and expanding the period distribution range.
Yeah, I also wonder about like astrometric wobble. So there are the resolved binaries, but there are the unresolved ones where the PSF wobbles back and forth. I don't know if anyone's tried to look for that in white dwarf systems or what period range that probes.
Yeah, do you mean it is similar to what I just said?
Well, were you saying just you're picking things over luminous compared to the white dwarf track, or a bad astrometric solution because of the wobble?
It's the wobble, yeah.
The
It does
wobble,
that.
yeah.
Oh, I see. Okay, yeah. I was thinking the same thing. I wasn't sure what you're saying when you put 2 plus 2 together. I thought you meant, because you should also see some over luminous sources, right? If you have 2 5,000 Kelvin white dwarfs, that's twice as bright as 1 5,000 Kelvin white dwarf in principle. The problem with that is, of course, usually one is much hotter than the other, and so it just falls on the white dwarf track normally.
Okay, so maybe let's slowly wrap up that topic and maybe ask one final question. Is there any particular project? We talked about a lot of ideas, but is there anything that this group as a whole could tackle? And if not, that's fine, that we let the coordinator then work on that. Look at that.
Yeah,
we had a lot of ideas.
I have a thought there, but if there's who's the coordinator on this project? Because I'll send an email just to, I don't want to take up time so we can talk about instruments here, but who's the coordinator on this particular bit?
That's the one where you don't have one, I think. I don't know. Honestly.
Okay, great. So if I send an email, that'll effectively volunteer me. So
you send an email to Heis.
Yeah,
send an email
I'll send it to Heis. Okay, fair enough.
We have one.
Oh, there's Camilla.
Yeah, hi. So I just wanted to add, for the multiple project that we are trying to dig out a planetary companion to double white dwarfs. So that's something on the side, but it's still to be considered for the pre-EM. I just wanted to highlight that with Sylvia and with Andres and Valeria, we are trying to figure out exactly the parameter space of this kind of planetary systems that maybe can help as well to constrain the binary evolution. So we are doing that with TRES, but adapted for planetary objects. So the idea is to have an idea of the final planetary distribution around double white dwarfs, and then effectively try to start discussing indeed which kind of instruments and how we can detect the triple planetary system in that case. So at the moment we have a preliminary results that 20% of the planets can survive evolution, the binary evolution, which is quite good. And it's still preliminary results with a population, a small population, but we are going to increase it and test different common envelope evolution and test different planetary distribution, initial distribution for the main sequence injection. But I just wanted to bring this to the table because I think it's something that could be very interesting to develop as well together within the multiple project.
Yeah, for sure, absolutely.
I just fully want to second what Camilla just said. I think these planetary companions and also stellar companions are really super interesting, and yeah, it would be great to actually brainstorm about what can be done for these sources. I mean, keep in mind that if you look at binaries in this mass range, at least 1 in 4 binaries starts with a third companion, right? So
yeah,
actually at least. So the number I'm giving is for solar type stars. So likely in the white dwarf range, it's even higher.
Yeah, so I should note, I've also been thinking about this from the observational perspective, because I realized if you had a shortish period triple where the outer companions in, say, a 4 or 5 hour orbit, the timing residuals it would introduce would make it extremely difficult to pick up the inner binary in a period search, even if it were emitting periodically. So what I've done is developed an algorithm that basically takes into account sinusoidal timing residuals from an outer companion to try to specifically target systems with this phenomenon happening. with a large amplitude timing residual. We're also monitoring a lot of the sources that we found, both the ones that are a bit too long period for LISA, but also the ones in the LISA band, to look for orbital decay. But the hope is at least a few of them may actually show a signature of an outer companion, whether that's a planet, a neutron star, a black hole. Probably not stellar companions, because if there is a G-type star there, you would see it. It's going to be brighter than the double white dwarf. So you're going to bias yourself towards these very low luminosity objects.
Yeah, that can be any substellar object, right? So
yeah, exactly.
Yeah, we should talk about that a little bit, Kevin. Jason Steffen and I had thought about this several years ago. Because he's the one who worked out transit timing variations for finding multiple planet systems in transit surveys. So we should talk and see if there's something interesting there.
Yeah, the nice thing is with the double white dwarfs, you get so many transits so fast. It's almost like a pulsar. You're sampling it so well.
The thing is, like from the preliminary results, like we don't have like close-in objects.
Right.
And as well, like the inclination of the system is far away from transit. So literally there is a peak at 65 degrees. So I think transit will not be, from what we're seeing at the moment. Obviously, we are trying to to check all over the possible outcome of the population. But technically, I don't think like transit is going to be like the method to use for this kind of detection. Also, as you said, like you will need like a very high sample, because like if you, I'm talking about giant planets, right? So giant planets will eclipse like totally your double white dwarf in a second. So it also depends on the separation and so on, but I see the probability very, very low for transit.
Yeah, well, I wouldn't expect the planet to transit, but the hope is if the inner binary is transiting, you can use the timing variations of the eclipses of the two white dwarfs.
Yeah, okay.
Yeah, so those are actually a great clock for doing this kind of thing. It's exactly what the pulsar people do to basically measure the projected semi-major axis of a companion to the pulsar.
Yeah.
But you'll get timing variations in the gravitational wave data as well. You should, right? I think that's what Jason and I were worried about. So yeah.
And so, for example, for the 7-minute system, we're pretty sure that there's you're pretty sure that there's no third body around it.
Not in less than about a 10-year orbit, but there could be a very long period third body that's actually mimicking the orbital decay, and we may actually have the chirp mass wrong because there's some contribution from a black hole in a 100-year orbit or something. That's something we have to reckon with. But it's a powerful technique, right? The first exoplanet candidates were found around pulsars using exactly this kind of technique, right?
Yeah, exactly. Yeah, so it's important that we monitor our known systems over the next years, not just a data point every 5 years because we think it's all fine. Monitor regularly to make sure we keep a good, right? Kevin, would you agree?
Exactly. Don't just assume it's a parabola. It may have a wobble in it, and that wobble is a very, very valuable piece of information.
One other point is we just work with Michael Katz to see and Tyson to see exactly what would change if we assume that the binary system is a binary and instead it's a triple, and sometimes you might have an offset of the termination of the gravitational waves, so it can be very far away from the true value of the binary, and so having like the chirp mass completely off. So we need to account that there might be a triple, like a third object in the system, of course.
Yeah, it's something I worry about a lot, and it's very difficult, unfortunately, to determine it for long period third objects.
So I have actually a question. How well do you know the verification binaries? Because you guys studied it for a long baseline? I don't know, because I was wondering if maybe one idea could be to target those objects if you have if no studies have done for a long baseline to see if actually there might be something else around it.
Yeah, so that's exactly what we're doing. The challenge is you need fairly big telescopes to do this kind of timing, and we keep building up more and more systems, and that's trying to decide what to point our limited resources at, which is one reason I jumped in on being the lead on the instrument development side, because there's so much more science we could be doing if we had more facilities to target these objects with.
It's maybe a bit of an obvious question, but has anyone cross-matched the verification binaries with Gaia? Because there's been quite some tertiary companions that we found through that.
Yeah, I did. There aren't very many of them. Yeah, I haven't found any like common proper motion companions or anything. Though I haven't looked at things like their astrometric wobble. That could actually be an interesting thing to test.
Yeah, so Sylvia, slightly related. So the sample of 800 white dwarf main sequence eclipsers, I did cross-match to check for common proper motion stars, and there's about 4 of them which have like an obvious detection. So it happens, but it's rare.
4 out of?
4 out of 800.
Oh yeah, that's rare. Cool.
So maybe we are running out of time, but I want to very briefly at least jump on the last topic on instrumentation. Is there any obvious thing we want to make sure we're not missing? We're starting right now. Is there any obvious project we want to start as a group right now and not forget, and then say, oh shoot, we forgot that, or we missed that deadline or whatever?
Well, I mean, the deadlines, one thing that's coming up are the ELTs, right? Not all of them with certainty, but we may want to get a LISA-oriented follow-up instrument, at least one on one of the ELTs. And to my knowledge, currently, I've looked at the proposed instruments, there's nothing like that planned. That could be something simple like a high-speed photometer, basically a hypercam clone. Vic actually tried to put in a proposal for one and it got rejected. It could be a frame transfer spectrograph type instrument so that we can actually do phase resolve spectroscopy on these things. I was going to show, I've actually been doing some tests on Magellan, kind of developing this capability. And we're now talking with one of the people developing the flagship spectrograph for GMT, Warren Brown and I are about implementing this. But what I call it is typewriter spectroscopy. And I don't know how many of you are familiar with spectrographs, but I'm going to show you a DS9 image now. So do you see all these horizontal bars? That's light let through something like a 4 arc-second slit on Magellan. These are flat fields. And the idea is you can clock charge on CCDs very precisely. So if you know the orbital frequency of something, what you can do is say, integrate for 10 seconds, shift the charge up 40 pixels, integrate for 10 seconds, shift the charge up 40 pixels. Keep doing that until you run out of room on your CCD, and then shift the last trace back down to into the slit and keep accumulating signal at the same orbital phase. And you can do this without reading out. And one of the big challenges with all these LISA binaries is that they're so faint that if you try to do spectroscopy on them with short exposures, you get completely drowned by readout noise. The reality is, even on an ELT, you can't take a 10-second exposure of a 25th mag star. There are just not enough photons to get over the read noise floor. But there are clever tricks you can play like this to avoid reading out and actually build up enough signal to noise to do something. And this is not a capability that most people think of, but it's actually something that's not hard to do on most spectrographs. And so what I'm trying to push is to make sure that we have capabilities like this on the ELTs, because there will be a handful of really, really exciting LISA binaries that we get when LISA turns on. And many of them are probably going to be 8 kiloparsecs away near the galactic center behind a bunch of dust. And so the question is, do we actually have an infrared spectrograph capable of getting through that dust and building up enough signal to noise to do something useful with these sources? I'm in particular thinking, like, say we find a binary where it's like this thing could merge in the next 10 years or something and explode in a type 1A. It would be a shame if we had no follow-up facilities to actually look at that thing before it exploded. And so my objective is to kind of think about the best facilities for the population of sources that we'll get with LISA. And the good news is we can already test them out on the sources we're finding now. And LSST is going to take us into much fainter territory where it'll really start to exercise the limits of what we can do right now in terms of follow-up.
So maybe I think maybe let me add on that. That's actually to me the perfect kind of thing for a group like we are, because having a large group community behind it produces much more push on the people deciding that, right? If they see, oh, there's a large community behind it. So I think that's something, Kevin, I think you should use all of us as a kind of one resource, but also as a kind of community to help get this done. And if it's a telescope, which is maybe because your area is not accessible to you for whatever reason, use people in Europe to help you get on that. So really, I encourage you, when you've been as a leader of this group, use everybody to push for that. And we
yeah, exactly. And this is one thing where, as you mentioned earlier, this is not a student project. It's important to have more senior people with faculty positions helping push this. So we need to build the momentum or it's not going to happen.
Exactly.
And yeah, I'm pretty much targeting every ELT we can. I think we should go for the European ELT. We should try for GMT. If DMT ever gets its act together, we should also push for something on that. These are going to be a very finite resource, and the people working on the instruments right now are mostly not LISA people, and they're not realizing that this is going to be kind of the highest impact science in astronomy 10 years from now.
Yeah.
Can I also add one thing? With all these ELTs being built in the next decade or so, there will be lots of time that becomes available on the slightly smaller but still useful telescope. So it might be good to not forget about the VLTs and the KECs, make sure that we also have, because there we can get an instrument on and we can use it for a much longer time, or get much more time on it. Because the competition will be fierce for the large telescope. And LISA will detect many double white dwarfs. So you should also think about if you want lots of time on like 10-meter telescopes or just a little bit of time on that.
I fully agree. There's a lot of work to be done on existing telescopes right now as far as improving the instrumentation.
Yeah, and that's something where institution-specific investigators, I'm going to start encouraging too, like look into the possibility of, can you put in a proposal for an instrument, for example, a high-speed photometer, because those are not particularly expensive or difficult to build. Well, it depends on what kind you build. If you try to build Hypercam, that's a $5 million instrument. But something like Chimera, which we've used on the Hale to great success, that was a few $100,000.
Exactly.
Yeah,
and we have nothing like that on Keck right now, for example.
Yeah, so that's what I'm thinking out from the European side. We've got 4 VLTs, and UltraCam has already been mounted on one of the VLTs already. So it would be great if that could be done permanently once the subscription rate slightly decreases for the VLT.
Yeah, and I find one of the pushbacks for a lot of these things is people go, well, you have Hypercam. Why do you need UltraCam on the VLT? And it's like, when you build a spectrograph for the VLT, I don't hear people saying, oh, but you already have LRIS on Keck. Why do you need a spectrograph for the VLT? People just dismiss these as unimportant instruments. And it's like, these are going to be the bread and butter science instruments in the LISA era. And the reality is right now, we only have like 2 or 3 good ones in the entire world.
So with that, I think we had a great discussion. Sorry, we have to close, but I think it was a great discussion. We have lots of ideas. I made tons of notes. I will put them in the Google Docs, send them around, have you add that to that. And then hopefully from that, we find leads who really take on this project and then really start actually working on those projects.
So one last question, Thomas. One last question. Are there regular telecons for this group that we can participate in?
Not right now. This was kind of not, but that's hopefully guys will make sure to have this happen.
Okay, perfect.
Thank you.
See you all in the other room.
Yeah. See you in the other room.